This instrument is a polarimeter. With it, we can measure the optical rotation of any optically active substance in solution that we can put into it. And we're going to do an experiment in this instrument, and what we're going to do is we're going to look at the action of aqueous base on a chloride, in fact this chloride, 1-chloro-1-phenyl ethane. And you may notice one thing about this chloride, namely that it is a chiral chloride. That is to say that it exists, or is capable of existing, in optically active forms, one of which rotates the plane of polarization of plane polarized light to the right, and the other one rotates it to the left, one in a clockwise, one in an anti-clockwise direction. We are actually going to carry out our experiment on the one that rotates in an anti-clockwise direction. And as you can see from the readout here, that implies that the rotation has a negative sign, and as you can see, the reading at the moment is minus 34 degrees. Now, we're going to carry out this reaction here, the action of aqueous base on this chloride. Now, we have not in fact dissolved up our base just in water alone. We have dissolved it up in a mixture of water and acetone, and the reason for doing that is in order to make the solution homogeneous. If in fact we tried to dissolve it all up in water alone, all the chloride wouldn't dissolve and we wouldn't have a homogeneous solution. So we use some acetone as well. Now in this reaction, you're attacking with OH minus on the carbon, you're displacing the chlorine and getting the OH taking its place. This reaction is not a particularly rapid one. In fact, it will take some time to accomplish, but as we have already put the base in the polarimeter here, the reaction has already begun, but you can see it's fairly slow in terms of the readout is just beginning to go down a little, but it does go down fairly slowly. Now, while that reaction is going on, what I want to do is to talk to you in rather more general terms about the implication of reactions like this one that we are studying. When we want to study a particular chemical reaction in some detail, one of the first kind of measurements we seek to make is kinetic measurements. What we're actually doing then is we are monitoring the rate at which the reaction actually proceeds by observing the rate at which the concentrations of, say, the starting materials decrease, the rate at which they disappear, and then having monitored the actual rate of the reaction in that kind of way, we find out what exactly is the relationship, the mathematical relationship between that rate and the concentrations of the starting materials. And that relationship we call the rate equation. There are a couple of examples of them on the board here. Now, this prompts the question about what does the rate equation actually tell you about a reaction? Well, what it tells you is it's a kind of catalogue of the species that have been involved in the reaction up to and including the overall vital step in the course of the reaction. Now, in the reaction that we have been talking about here, where we are talking about the way in which a chloride reacts with OH minus, what we're doing, of course, is we are attacking the halide with OH minus, and a reagent like OH minus is commonly referred to as a nucleophile. And what we're doing with this nucleophile is we are attacking the carbon atom of the halide and displacing the chlorine atom originally attached to it as a chloride ion. So it's a substitution reaction. So we call the overall process a nucleophilic substitution. And we generally sort of have a shorthand for that of calling it an SN reaction, so that that particular rate equation represents an SN reaction, a substitution, a nucleophilic substitution reaction. What we have got here is the S, of course, is standing for substitution, and the N in each case is standing for nucleophilic, substitution by a nucleophile. Now, what I was just saying about the rate equation was that it tells you, it spells out for you, all the species that have been involved in a reaction up to and including the vital step. Now, what we're going to do now for you is we're going to use extremely simple models. In fact, we're going to use snooker balls to illustrate for you the vital step in each of those sequences we saw a moment or two ago of rate equations. And for a demonstration involving snooker balls, who better to do it for us than Dennis Taylor here? Welcome, Dennis, to Chemical Snooker.
Thank you.
Let me tell you what, in fact, we're now going to do. I think, first of all, we're going to have a look at the process corresponding to the first of those rate equations, in which both the chloride and the hydroxyl ion were involved. And I'm going to put these balls out here in the middle. The black one is for carbon, as you can see, with the C on, and the green one has got Cl on. And I'm going to put them close together like this. There's the halide. Now, what you're going to do, Dennis, here is the attacking OH minus, is you are going to cue that in the direction of the chloride here and hitting the black carbon atom, and you will see the red hit the black carbon and become attached to it, and the green chloride ion move away. Now, let's have another look at that, but a bit more slowly and a bit closer to. And at the moment of impact, all three of the balls are in fact in contact. Now, the reaction pathway that you've just seen was clearly a one-step process. It was one step that involved both species, both the halide and the OH minus, in the vital step of the reaction. So we call this reaction, or this pathway, SN, substitution nucleophilic 2, and the 2 to indicate that both species, both the halide and the OH minus, are involved in the vital step. But now what about this rate equation? Now in this one, clearly, according to the equation, only the halide, only the chloride is involved in the vital step. So let's now go and see what we can make of that in model terms. Now we're now going to see what happens according to the second of those rate laws. Here's the same halide again with the carbon and the chlorine. Now what we're going to see this time in the vital step is we're going to see the chloride moving away from the carbon in a do-it-yourself operation, an actual ionization of the halide as the vital step. There it goes. Now, as an entirely separate step, here is Dennis Taylor going to take his attacking role once again, and he's going to cue the OH minus, the hydroxide ion, up the table to join it on to the carbon atom to finally make the product. Now let's have another look at that a little more closely and a little more slowly, that what we're seeing is quite clearly two events taking place. The first step, the vital step, in which the chlorine is departing from the carbon atom as a chloride ion. That's the first, the vital step. And then subsequently, as a quite separate operation, we're getting the OH minus coming up and becoming attached to the carbon atom to form the final product. Now, the reaction pathway that you've just seen was clearly a two-step process. But because in the vital step, that's in fact the first one, only one species, the halide itself, the chloride, is involved in a do-it-yourself operation, because only one species involved in the vital step, we call this reaction a nucleophilic substitution, SN, we call the pathway, but SN1, 1 to indicate that only one species is involved in the vital step of the overall reaction. Now, as you're probably already saying to yourself, there's some element of a paradox in this, in that what we have got here, we've got the first case, the one we looked at to start with, that, you remember, was a one-step pathway, but because two species, both the halide and OH minus, were involved in the vital step, we call this a substitution nucleophilic 2, whereas in this case down here, which was a two-step pathway, but because only one species, the halide alone, is involved in a do-it-yourself operation in the vital step. We call this pathway substitution nucleophilic 1. Now, obviously, the snooker ball models that we've been talking about up to now have clear limitations. Not the least of these is the fact this is not the kind of form in which we normally think about organic molecules. A form, however, of model that we do use and think regularly about organic molecules in terms of is this kind of model here, this ball and stick one. And you can see what we've got is here in black is the central carbon atom. Here is the chlorine attached to it in the chloride, and these three greys round here are just indicating other sorts of groups. And here we have got the OH minus, the hydroxide ion that is going to attack it, and what is going to happen here is you're going to get attack, of course, by the hydroxide ion on this carbon. But let's now look in a little more detail at actually what happens to this model when we're talking about the SN2 pathway first of all.
As the hydroxide ion approaches the molecule, a bond begins to form between it and the central carbon atom. This is accompanied by a weakening of the carbon-chlorine bond, resulting in an increase in its bond length. At the same time, the umbrella formed by the three other groups begins to flatten. The point at which these three groups all lie in the same plane is called the transition state. Notice that the central carbon atom is attached to a total of 5 groups. A new complete bond forms between the hydroxide ion and the carbon, while the original bond between the carbon and the chlorine is completely broken. In the product, the umbrella is now turned inside out.
Now here we've got the product alcohol. As you can see, what's happened is the red OH minus is now attached to the back. It's come in from this side. The three grey balls, which were originally facing sort of that way, their umbrella has been turned inside out and now facing the other way. And here is the chloride ion, which of course is departing, was attached to there and is now departing. And over here we've got what is really an energy chart of the trajectory, if you like, of the reaction. That we're starting off here with attack of OH minus on the carbon of the chloride. We're proceeding up there, attack from the back by OH minus here in the transition state corresponding to this energy peak here. You've got OH minus becoming attached to the back of the carbon atom, and you have got chlorine beginning to depart as chloride ion from the front, and then down the energy hill it comes again in order to produce you the product alcohol and the chloride ion that is departing. Now, let's now look again at this SN2 process in which we're watching what is happening to the models, and at the same time we're traversing this energy diagram as the models are moving along.
As the hydroxide ion attacks the carbon atom, the energy of the system increases, reaching an energy maximum, the transition state. Loss of the chloride ion is accompanied by a decrease in the energy of the system.
Now let's come back to our chloride once again, and this time let's see what happens to it if it were reacting by the SN1 pathway.
The vital step is ionization of the molecule to give the flat intermediate. Consequently, in the second step, hydroxide ion can attack from either side. Let's see what happens in each case.
Well, here we've got the products from the SN1 pathway, the product alcohols, one of them obtained by attack by OH minus from one side of that planar intermediate, the other by attack by OH minus from the other side, and I think, as you can see fairly clearly, they are, of course, hardly surprisingly, the same product. Now, if we now turn to this energy chart for this process, for the SN1 process, you can see straight away, of course, that it does indeed involve 2 steps. The first of these steps involving just the chloride alone, in which you're getting the do-it-yourself ionization of the chloride to form these, And this, of course, the R plus is the planar, the flat intermediate. And in the second step, you're getting attack on this flat intermediate, either from one side or from the other side by OH minus to give you the product alcohol. And what we're now going to do is to look again at what is happening to the models during the course of the SN1 reaction, and at the same time, we're going to traverse this energy diagram so you can see what corresponds to what.
Ionization of the molecule is accompanied by an increase in the energy of the system to give a flat intermediate. From whichever side hydroxide ion attack occurs, the energy of the system decreases as the product forms.
Now let's have another look to see how our experiment is going on. As you can see, the readout is now minus 12 degrees. It's moved down from the minus 34 degrees that we started from, but as you can see, it is in fact still slowly going down. So what we can say is that the reaction is still not finished yet, is still going on. Now, in the models we've looked at up to now, in following the course of SN2 and SN1 pathways for nucleophilic substitution, we've been dealing with quite simple halides, quite simple chlorides. But of course, we're actually carrying out our experiment on a chiral chloride. And here I've got a model of this chiral chloride, in which here is the black carbon atom, here is the green chlorine, and then I've got three balls round here representing the different groups, an orange one here, a yellow one there, and the grey one over here. And what we're now going to do is we're going to follow through on this now chiral model what is going to happen, first of all by the SN2 pathway and then by the SN1 pathway. But first of all, let's see what happens by the SN2 route. Well, here's the product from the SN2 pathway on our original chiral chloride. As you can see, it is, of course, an alcohol. Here's the red OH at the back. And, of course, it is a chiral alcohol in the sense we've got three different groups apart from the OH attached to the carbon. So the product here, will have an optical rotation just as the starting material did, the halide we started from, that was chiral 2. So in the polarimeter, what's going to have happened if a reaction has gone by the SN2 is starting with an optically active starting material, we're going to end up with an optically active product also, although presumably its actual value, its actual extent of its optical rotation is going to be different, the product from the starting material. But now let's go on, and now let's go back to the halide and let's see what happens to it by the SN1 pathway. Well, here are the products from the SN1 pathway on our chiral halide. As you can see, we've got a chiral alcohol. Here's the OH, there's the OH, and so on. What we've got, one of them, of course, we've got from attack on from one side of that originally planar intermediate. The other one we've got attack from the other side on that originally planar intermediate. And the first point of interest is, are they in fact actually same as each other or not? Well, let's put them around this way and have a look. And I think you can see, if you look at them reasonably closely, that they are indeed mirror images of each other. You can draw a mirror plane down here, and then yellow is facing yellow, orange is facing orange, grey is facing grey, and red is facing red. These are in fact mirror images of each other. So far as what we might expect to happen in the polarimeter is concerned, provided indeed that you get equally easy attack from one side or the other side of that planar intermediate, 50% from one side is going to lead to 50% production of one chiral alcohol, rotating the plane of polarization in one direction. Attack from the other side is going to lead to 50% of the other chiral alcohol, rotating the plane of polarization in the opposite direction. So the net effect, provided one did indeed get a 50-50 ratio, is going to be no net rotation observable in the polarimeter at all. That's from the SN1 pathway. Now let's just recap for a moment as what, therefore, we can expect to happen. If this hydrolysis of our chiral chloride has gone by the SN2 pathway, then what we're expecting to get is an optically active alcohol as the product at the end, so we expect to see still optical rotation recorded on the polarimeter, though the value, of course, almost certainly different from what we actually started with. Whereas if, in fact, this reaction has gone by the SN1 pathway, then what we're expecting to see is no net rotation at all, because the effect of rotation of these two species has cancelled each other out. So now, with that as background, let's go over to the polarimeter and see what indeed has actually happened. Now, in this case, you can see that the result is quite clear-cut. You can see in the readout that there is, in fact, zero net rotation, none at all. So we can say with some confidence that our initial chiral chloride, this one here, the 1-chloro-1-phenyl ethane, has indeed reacted by the SN1 pathway. Now, I think one has to say that the results, even from the SN1 pathway, are not necessarily always quite so clear-cut as this. It depends, of course, whether indeed in attack by OH- from the one side or the other side of that flat intermediate does indeed take place in an absolutely 50-50 ratio. If it does, of course, there is no net rotation, as happened in this case, but sometimes, for a variety of reasons that are mentioned in your Unit 7, you don't, in fact, get an exactly equal attack from the two sides, and there may then, even with the SN1 pathway, be some residual optical rotation in the solution. Now, you may perhaps be saying to yourself, well, we've now studied at least one reaction, the mechanism or the possible mechanisms for it in some detail, and are asking the question, well, all right, having done so, you know, what good does this kind of study, this kind of activity do you? And I think one can really say two things about this. On the one hand, it very often helps you when you're contemplating doing a reaction in preparative terms. You want to get as high yield as possible. It often helps you to choose what are going to be the most satisfactory conditions in order to get as big a yield of what you're after as possible. And you'll be hearing more about that kind of thing when you come to consider elimination reactions quite shortly now. I think the other way in which it can be useful is when you're coming to actually design and plan the synthesis of perhaps quite a complex compound, which is going to involve a whole series of reactions. By thinking about the actual mechanism by which these various stages proceed, you can often decide to carry out your synthetic procedure by one set of reactions rather than by another set, because knowledge of the mechanisms allows you to make an intelligent choice in terms of which is likely to work the best of the two. But finally, I have to confess that I am myself interested in mechanism of reactions just because, and for no better reason, than I find it an extremely fascinating study entirely for its own sake.